Okay, the last of our 4 lessons based on lesson 100 in our book, Quadratic Applications Part 2. And what we will really be focusing on today will be vertical motion, where something is thrown into the air or dropped from a certain height down towards the ground, or maybe something is shot and it goes up in the air. Vertical motion is also sometimes called projectile motion, and as long as we are talking about initial velocity and height, and as long as we are talking about feet and seconds, physics has shown us that the equation is the height at time t in seconds is -16. That comes from gravity pulling the object back down. That's why it's negative, meaning going in a negative or downward direction. T squared plus v naught, that is a single variable, just like we've seen subscripted variables in many of our other problems. That means initial velocity velocity is basically speed, and initial means at time 0. And then we have h sub 0, that's another subscripted variable, that is the initial height. It's the height at time 0, it's the starting height. Maybe we are up on a platform when we throw something or drop something. Notice that if we are drawing a graph of this, maybe we start at initial height and it goes up. Now this is time. This is not how far away. This is throwing something straight up in the air. So if I did the horizontal distance over here, I might be starting someplace, throwing it straight up, and then it comes straight down. If I'm on a platform, it's just going to stop when it hits the platform, but maybe I've reached my hand out over the railing and I throw something up and release it, and then when it comes straight back down, it misses the balcony I'm standing on because it's going out past the railing, and then it would come straight back down until it hits the ground. So now we're going to talk about if this is time and how much time it takes, and this one is what our graphs will look like for these types of problems. So maybe we start, and after, when we start, and leaves it up to us to interpret what is going on. So if this is height, when we are at a height of 0, so this means 0 seconds right there, and it means 0 height or ground level. Time is 0, height is 0. This point over here means at some particular time, we get back to ground level. So this is at another time and back to ground level. So let's move on to our first example. So the world record for the World Championship Chunkin contest, yes, there really is such a thing, held each year in the state of Delaware, is held by an air cannon named Second Amendment. So basically they have a whole bunch of different cannons, different people have designed them, and they're competing to see who can shoot it so that it stays in the air the longest. And then there's also another equation that deals with the horizontal distance of how far away it shoots it. And they have contests to see which cannon is the most powerful, does the best job with it. And so for this one, This describes, again, just the height. This is not talking about how far away from the cannon does the pumpkin go, but this is just talking about if we just looked at the vertical part, it goes up for a little ways, and then it starts to come back down. H of t equals, there's our minus 16 again, t squared, plus 880t plus 70. So this fits our model of h of t equals negative 16 t squared plus our initial velocity times plus our initial height. So that tells us that it started off 70 feet above ground. These are gigantic cannons that shoot these things. This also tells us that we had an initial vertical velocity of 880 feet per second. So let's see what this problem wants us to figure out. After how many seconds will a pumpkin shot from this machine land on the ground? So let's think about what's going on here. I'm going to draw our graph, and when we know that initial velocity, I expect you to label that on your graph. It's going to start out here at 70 feet high, and it is going to go up for a while, and then it's going to come down, and it's really going to stop when it hits the ground. It's really not going to keep on going. We want to know after how many seconds will it land on the ground. Oh, we want this point right here. That's when it lands back on the ground. So let's enter this in the calculator, but on the calculator it's going to be entered as F1, and we're going to put in X's because the calculator does not read T's the way we need it to for this. So we're going to enter negative 16x squared plus 880x plus 70 as we enter that on the calculator. So let's give that a try. So I'm on one of my graphing Scratchpad pages. So I need to hit tab so I can enter that function that I just wrote down. And remember, we just said we were going to do it as negative, so we use that negative button, not the minus. 16x squared plus 880x plus 70, and hit enter. And I'm only seeing the part of it that's going straight up, and I've got to change the window. What in the world might be wrong with that? Well, I know that it's got to start at 70 and go up a bunch more and then come way back down. So this one we are going to change the window on. So we're going to do menu, window zoom, and I'm going to do window settings this time and try to guess some things to put in there. So let's put in for our X-Men, just so that we have some room to work with over there if we need it. Let's change that maybe to negative 50. And then my X maximum, let's put maybe 100 in that one. Don't worry about X scale, just leave that as auto. Go down to Y minimum. And I want a little bit of room to work with underneath the y-axis so it doesn't totally disappear on me. So let's call that maybe negative 50. And then I really need this one to go way up high. So for my y max, let's put in 15,000. So now I'm getting where I can kind of see it, and I hope that I actually had enough that it's going to let me get those x-intercepts. So maybe I need to change that and go even farther than that negative 50. So let me click on it, and let's see what happens if we go to negative 300 maybe. So negative 300. Okay, now I feel like I can at least see it. And what I know that I needed was this point right here. So I'm going to do Menu, Analyze Graph. This is a 0 that I'm looking for, left and right, and it gives me something kind of strange looking on my coordinates there, doesn't it? Now, a couple of things. We require that you show us a sketch on all of these word problems. On my calculator screen, it looks like my parabola goes through 0, 0. But it is not okay with me if you draw one that goes through 0, 0, because in the context of this problem, you know that it has to start at 70 because of that plus 70. So I am going to count it as a mistake if you don't have that 70 marked on there, and if your parabola looks like it is starting going through 0, 0 instead of 0, 70. So now our calculator told us the x-coordinate of this is 55.0794, so I'm going to round that to 3 places, 55.079. And this one simply asked me for, after how many seconds will it land at that point. So to answer this question, I can say 55.079 seconds. I am going to label my coordinates here on my sketch as 55.079, comma, and then it had that thing in exponential notation, didn't it? Negative 1.79, or negative 1.979 times e to the minus 10. Well, that means I've got a teeny tiny number, 0.00000, all those zeros before I even get to the 1.979. It should be comma 0 if it is an x-intercept. And that's how we are going to label it on the graph, even though it shows that teeny tiny decimal on the calculator. The reason for that just has to do with how the calculator is programmed and how it finds, and the process by which it finds that. It doesn't always land exactly on 0 in the algorithm that it needs to use, but we know that it should be a 0, so that's how I expect to see this problem labeled in your work. Okay, let's see what else this problem asks us for. Will it reach 11,000 feet? Okay, feet, that's what goes on my y-axis, and I want you to label your axes too. So this is going to be your height in feet. And this axis, you must always label time in seconds. Well, there may be some problems where it is something different, but you always need to label what it is. Your vertical motion ones, it will be time in seconds. So feet, that's going to be on the y-axis. That means we want to know, does it get to a place where y is 11,000? So we are going to draw a horizontal line on our calculator graph where y is 11,000. So tab, and then we're going to do that f2 of x equals 11,000, enter, and it does go through there. Now, if your scale was such that you couldn't tell if it was right on the vertex or above or below, you would need to menu, window zoom, and zoom in so that you could tell that just a little bit better. Don't really need to on mine since it shows up well enough. So, will it reach 11,000 feet? Yes, it will. It will actually reach it twice. It will go through 11,000 feet and keep going up just a little bit, and then it will hit 11,000 again as it comes down. So if I want to know when it will reach 11,000 feet, then I need to do menu, analyze graph, but now I want to know where the parabola and the line cross or intersect. So I'm going to go to the left and to the right, and this tells me it gets to 11,000, see that y-coordinate, at 18.949 seconds, and menu, analyze graph, intersection, left and right, and it hits 11,000 again, see the y coordinate, at 36.051 seconds on the way down. So will it reach? If so, when? So yes, it reaches 11,000 feet after 18.949 seconds. That was on the way up. And again, after 36.051 seconds, and that time it is on the way down. We need to add that onto our graph, and so mine isn't great to scale, but I need to draw a horizontal line that is higher than that 70 and below the minimum, and that it clearly looks like it's below the minimum. And then I label these points on my graph. This was 36.051, comma, 11,000. And this one was, what was it again, 18.949, comma, 11,000. And let's see what else it wants to know about this problem. What is the max, and what does it mean in the context of this problem? So we know that means we need to find the coordinates of that vertex. So now we are looking for our vertex right here. So we go back to our calculator, and we do menu, analyze graph. This time we want a maximum, so choice 3. But now the calculator's confused, because now I have two functions in there. And it doesn't know, well, do you want me to tell you the highest the red line ever gets? Well, we already know that's 11,000. No, we want to know the highest the parabola gets, so we just go to it and we click on it, and now it knows the parabola. So I click somewhere to the left of that vertex and to the right of the vertex, and I have the 27.5, 12,170. So I go back and write that down on my paper. So my max for this one was, where did it go? 27.5, comma, 12,170. And if I've got room, I'll try to put that on the graph here. 27.5, comma, 12,170. What does that mean in the context of the problem? So under our x-axis, our x's are time in seconds. Our y-axis is height in feet. So this is our time in seconds. This is our height in feet. So the sentence that we need to write is the maximum height, I'm going to abbreviate max, of the pumpkin is 27 point, whoops, looked at the wrong one, caught myself there, of the pumpkin is 12,170 feet. Boy, that thing goes high. Then we also need to say this occurs at 27.5 seconds. Must explain it for both variables. Questions from anybody? Right, next one. A sailor at water level in a boat beneath the San Francisco Bay Bridge shoots a flare straight up, and the height of the flare after t seconds is modeled by negative 16t squared plus 96t. With this plus 0 in there, that would mean the height that it gets to above the gun that it flares out from, so above the flare gun. but we want to fill some other things in for that. The sailor's hand is really 12 feet above the water, so if we put in the plus 12, this one then gives the height above the water. So here it's starting out at 12 feet. What is that? 12 feet above the water. The bridge is 220 feet above the water. So the sailor is below the bridge and shoots the flare straight up. Sounds kind of dangerous to me. Let's see what we're asked for in this problem. Use a graphing calculator to determine if the flare will reach the bridge. Are the people on that bridge in danger or not? So let's use our calculator to get the graph, and then we will draw a sketch of what we see. So the one that we are going to enter is the one above the water, because we're talking about how far above the water compared to the bridge that's 220 feet above the water. So calculator here, menu, 1, 4, yes, everything's cleared. Well, let's go back. I don't think we're going to want that 15,000. Let's just go back to our window zoom, and let's go to choice 5 for standard, and then we'll see how we need to change it from there. So tab to be able to enter our equation, and we need to enter negative 16, and we use x's, not t's, x squared plus 96 x plus, oops, didn't get it on tab there, negative 16 x squared plus 96x plus 12, and okay, I kind of see part of my parabola, not seeing it all. So I know that I'm trying to get up to that bridge that is 220 feet high. So I don't think that 6.43 is anywhere close to high enough. So I'm going to click on that one and change that to, well, I know I want to go higher than 220. So let's try 250. Maybe that'll be high enough. And enter. Oh, nice. Now I can see it in there. And there's the equation for my parabola. Got it over here somewhere kind of out of the way. I also want to put in y equals 220, because here's the bridge, and am I going to reach it or not? So tab, and then y equals 220, and this tells us that the flare goes up, and it does not get as high as the bridge, and then it goes back down, so everybody is safe. So we can answer this question with, it does not reach the bridge. And we are going to sketch our graph. So let's see what it looked like here. So remember, we know how high it started. It started at 12. So we are going to label that this is 0, 12 for that point. It is going to go up and then back down and then hit the water, and it does not reach the 220. So we do another line clearly above that vertex, and that is y equals 220. This one did not ask us to find anything else. We could have found, well, how high does it reach? We could have found its max. We could have found the time when it hits the water, but it did not ask us to find either of those. Okay, a tennis player hits a tennis ball straight up at a velocity of 40 feet per second. When she hits the ball, her racket is 3 feet above the floor. The ceiling in the gym she is in has a height of 25 feet. So we need to complete this function. We will not always be given it. So the starting height when she hits the ball is 3 feet above the floor. So we need a +3 in this one. She hits it straight up, so the velocity is positive because it's going up. So positive is up, negative is down on that velocity, and 40 feet per second. So we can fill a +40 in there. We want to know if it hits the ceiling, and if so, at what time. So our second equation is going to need to be 25. So let's go back to our calculator, and let's do our graph for this one. So menu, 1, 4, yes. Menu, window, standard, choice 5. 2 equations. So tab for F1, negative. Is it not entering? Negative 16x squared plus 40, don't forget the x, plus 3. And I need to get where I can just proofread before I hit enter. Yes, that looked like I typed it correctly. And then my second one was F2 equals 25. And right now I can't see what's going on. You probably can on yours already. But we are trying to figure out here, well, does it look something like it starts here at 3 and goes up and doesn't reach the ceiling? Or does it start at 3 and it goes up and here is the ceiling and it does hit it? So let me look at my calculator and see what's happening. And I know I have to be at least higher than 25, and I probably don't really need it quite as wide as that is on there. So I can change this one to maybe a -5, and this one to maybe a +5. And this one's the one I really need to change. Let's change it to, well, maybe it goes up above, so maybe I ought to change it to 35 and see. Whoops, it didn't take all of that. I think I clicked in quite the right spot. So let's try 35. And it does hit the ceiling. The ceiling is lower than the height the tennis ball would reach if there were no ceiling. Now, does this one ever reach the maximum? No, because the tennis ball is going to hit the ceiling, and it is not going to go through the ceiling and keep getting higher. It's going to hit the ceiling and come back down. So it's not really going to follow the whole path. It's going to stop at the first place where it hits the ceiling. So we know now that it does not behave like this, so we would not really have drawn that on our papers. And we are now interested in this point, because really what's going to happen is it's going to go up, and then it's just going to bounce back down from there. So we need to get that point. I don't have those dotted lines in there. So calculator back up here. We need to get that one intersection point. We do not need the other one because it makes no sense in the context of the problem. So menu, analyze graph, intersection, lower bound, so we go to the left of the point we want. We can't go so far to the right that we get both intersections in there. It's going to confuse it, just that one that we're interested in. And its coordinates are 0.816987, so we're going to round that to 0.817, and we see that 25 is indeed our second coordinate. So we label this on our graph that this is 0.817, comma, 25. And our answer, it's not enough just to label it, we need to put it with its units. So after 0.817 seconds. And then you have some homework, which is quadratic application problems, part 2. And the first one is a little bit confusing, so let's try to set that one up together. A fireworks technician wants a firework to explode 70 feet below the top of the gateway arch. And the gateway arch is basically a parabola, but we're not interested in its equation. We're interested in the parabola for the firework. All we really care about with the arch is that its height is 630 feet. The technician wants it to explode 630 feet below that, which means that we need to take that 630 and subtract the 70 from that. So 630 minus 70 gives us 560. So what we are going to do is to punch in f1 of x needs to be negative 16t squared plus 160t, and the firework is going to be shot from the ground. These are these high-powered, very dangerous fireworks that only the professionals set off, and they're nowhere close to them. They're hitting the controls to explode them all remotely, but it starts from the ground. That's why we don't need the plus 0 out there at the end. And then f2 of x, we want to know about it reaching the desired height. So f2 of x is going to be our 560. So I want you guys to do this on your calculators. You're going to, I think I was forgetting on some of these, I'll go back and do that. We're going to label this as time, and this is height. We know that this one, the firework, is going from the ground up and coming back down. We're interested in this vertex, and we don't know if we need to do the 560 up here above it or down here below it. That's what the calculator is going to help us figure out. And then we want to determine if it hits that 560 or not of what we want. We're not trying to figure out will it hit the bridge or not. We want it to get to 560 or not. So I will pause and let you guys do that on your calculators, and then we will check. So continuing, hopefully your graph looks something like this. Starts at 0, 0, it goes up. The height of the parabola is below that line where y equals 560. And let's copy our graph and answer our question here. And I am assuming that you knew this meant to actually enter it on your calculator with x's, negative 16x squared plus 160x. Just for our calculator to understand it better, we've got our axes labeled here, and here was the line at 560. And no, it does not reach 560 feet. And I said I was going to go back and label my axes on these other ones. So this one should have been, get everything that I need labeled here. I should have labeled my 3 on this one, and this was my height in feet, and this axis was time in seconds for for this one, I did get the 12 on there, and the Y that I also needed to label was, this one was time in seconds, and this one was height in feet. And back to example 1, I did get the labels on that one. So you guys continue working on quadratic applications problem part 2, since that is your homework set.